GenAI and MLOps Part 30. This episode has 5 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. What is feature freshness? Here's a strong way to approach it. Feature freshness refers to how recent and up-to-date a machine learning feature is when it is used for model inference or training. It measures the time difference between when data is generated and when the corresponding feature becomes available to the ML model. Feature freshness is especially important in real-time and streaming ML systems where stale data can reduce prediction accuracy. Example: in a fraud detection system, latest transaction amount and user activity should be updated immediately. If features are delayed by several hours, the model may miss fraudulent behavior. Why feature freshness is important: improves prediction accuracy, enables real-time decision-making, reduces stale feature problems, supports dynamic and event-driven systems, maintains model reliability in production. Common use cases: fraud detection, recommendation systems, stock market prediction, ad monitoring, personalized advertising, real-time analytics. Challenges: data pipeline latency, delayed stream processing, batch update limitations, distributed system synchronization issues. How feature freshness is maintained: streaming data pipelines, real-time feature stores, event-driven architectures, low latency ingestion systems, continuous monitoring and alerting. Popular technologies: Apache Kafka, Feast, Spark streaming, Apache Flink. Redis. From an MLOps perspective, feature freshness is a critical factor for ensuring real-time ML systems provide accurate, timely, and production-ready predictions. Nice. Let's continue. Question 2. Explain batch scoring pipelines. Here's a strong way to approach it. Batch scoring pipelines are automated workflows used to generate machine learning predictions for large volumes of data at scheduled intervals instead of in real time. In batch scoring, data is collected over a period of time and processed together in bulk to produce predictions efficiently. How batch scoring pipelines work: 1. Data is collected from databases, files, or data lakes. 2. ETL or pre-processing steps prepare the data. 3. Features are generated and validated. 4. The trained model processes the dataset in batches. 5. Predictions are stored in databases, warehouses, or reports. Common use cases: customer churn prediction, credit risk scoring, recommendation generation, fraud analysis reports, marketing campaign targeting, demand forecasting. Key characteristics: scheduled execution, hourly, daily, weekly. High throughput processing, cost efficient for large datasets, suitable for non-real-time applications. Components of a batch scoring pipeline: data ingestion layer, ETL or data pre-processing, feature engineering pipeline, model inference engine, storage and reporting systems, monitoring and logging. Benefits: efficient for large-scale processing, lower infrastructure cost compared to real-time serving, easier resource management, simplified orchestration and monitoring. Challenges: prediction latency, stale predictions between runs, dependency on data pipeline schedules, large compute resource requirements during execution windows. Popular tools and technologies: Apache Spark, Airflow, Kubeflow, MLflow, Databricks, TensorFlow. From an MLOps perspective, batch scoring pipelines are important for scalable offline inference, scheduled prediction workflows, and enterprise analytics systems handling large datasets efficiently. Great. Moving on. Question 3. What is pipeline caching? Here's a strong way to approach it. Pipeline caching is a technique used in ML and data pipelines where previously completed pipeline steps and their outputs are stored and reused instead of executing the same steps again. The main goal of pipeline caching is to reduce execution time, save compute resources, and improve pipeline efficiency. If a pipeline step receives the same input data, code, and configuration as before, the cached output can be reused directly without rerunning that step. Example: in an ML pipeline, data pre-processing step already completed earlier, no changes in input data or transformation logic. Pipeline reuses cached pre-processing output instead of running it again. Benefits of pipeline caching: faster pipeline execution, reduced compute and infrastructure cost, improved experimentation speed, efficient resource utilization, faster retraining and CI or CD workflows. Common pipeline stages that use caching: data pre-processing, feature engineering, dataset validation, model training, outputs, intermediate artifacts. How pipeline caching works: 1. Pipeline step execution metadata is stored. 2. Inputs, parameters, and dependencies are tracked. 3. System checks whether the same step was executed before. 4. Cached artifacts are reused if no changes are detected. Challenges: cache invalidation management, storage overhead, dependency tracking, complexity, risk of using stale artifacts. Popular tools supporting pipeline caching: Kubeflow pipelines, TensorFlow, extended Dagster, Apache Airflow DVC. From an MLOps perspective, pipeline caching is important for improving scalability, accelerating experimentation, optimizing cloud costs, and enabling efficient ML workflow automation. Alright, next question. Question 4. Explain DAG-based workflows. Here's a strong way to approach it. DAG-based workflows are workflow management systems where tasks are organized as a directed acyclic graph. DAG. In a DAG, directed means tasks have a defined execution order. Acyclic means there are no loops or circular dependencies. Each node represents a task, and edges represent dependencies between tasks. A task can only start after its dependent tasks are completed successfully. Example: in ML pipelines, a typical DAG workflow may look like data ingestion, data validation, feature engineering, model training, evaluation, deployment. Each step depends on the previous step. Why DAG-based workflows are used: manage complex ML and data pipelines, automate task orchestration, handle dependencies efficiently, improve scalability and monitoring, enable reproducible workflows. Key features: 1. Task dependency management. 2. Parallel execution support. 3. Scheduling and automation. 4. Retry and failure handling. 5. Monitoring and logging. 6. Workflow visualization. Common use cases: ETL pipelines, ML training pipelines, batch scoring workflows, CI or CD automation, data processing systems. Benefits: better pipeline organization, easier debugging and monitoring, efficient execution management, improved scalability and reliability. Challenges: complex dependency management in large pipelines, scheduling optimization, handling dynamic workflows. Popular DAG workflow tools: Apache Airflow, Kubeflow pipelines, Dagster. Luigi Prefect. From an MLOps perspective, DAG-based workflows are essential for orchestrating scalable, automated, and production-ready machine learning and data engineering pipelines. Let's keep going. Question 5. What is Airflow? Here's a strong way to approach it. Apache Airflow is an open-source workflow orchestration platform used to automate, schedule, and manage complex data engineering and machine learning pipelines. It is widely used in data engineering, DevOps, and MLOps for building DAG-based workflows. In Airflow, workflows are defined as DAGs, directed acyclic graphs, where each node represents a task. Dependencies define execution order. Tasks run automatically based on schedules or triggers. Key features of Airflow: 1. Workflow scheduling. Run pipelines hourly, daily, weekly, or event-based. 2. DAG-based orchestration. Manages task dependencies efficiently. 3. Scalability. Supports distributed execution across multiple workers. 4. Monitoring and logging. Provides UI for tracking pipeline execution and failures. 5. Retry and failure handling. Automatically retries failed tasks. 6. Extensible architecture. Integrates with cloud, databases, Kubernetes, Spark, and ML tools. Common Airflow components: scheduler, web server, metadata, database, executor, workers. Typical MLOps use cases: ETL pipelines, feature engineering workflows, model training, orchestration, batch scoring pipelines, CI or CD automation, data validation pipelines. Popular integrations: Apache Spark, Kubernetes, Docker, TensorFlow, MLflow, Amazon Web Services, Google Cloud. Example: workflow, data ingestion, validation, feature engineering, model training, evaluation, deployment. From an interview perspective, Airflow is commonly used to orchestrate and automate end-to-end ML and data pipelines in production environments. On to the next one. That wraps up this episode. Nice work practicing, and see you in the next one.